So in the nucleus, we have the 2 protons and 2 neutrons. This would be for a helium nucleus here. And we know that the 2 protons do not want to be together. We have the electrostatic repulsion between those two. We know, force equals K Q1 Q2 over R squared, Coulomb's law. And those particles want to be apart from each other. So huge question here is, why does the nucleus not want to blow apart? And so there must be something stronger than the electrostatic repulsion, those two particles trying to get away from each other. So it turns out it's the strong force, and the strong force is sometimes called the strong nuclear force, that is responsible to hold the nucleus together, which is represented by these arrows pointing inward between the particles. And so the strong force is many times greater or many times stronger than the electrostatic force. And it's again another fundamental force here that is holding the nucleus together. So as we talk about the fundamental forces, we've talked about the force of gravitation, and we think about the force of gravitation. It's a very small force, right? It's a very weak force. We used this simulation way back, and in this simulation we can see that even if we have a decent amount of mass here, the amount of force is very, very tiny. I just crossed that one out, but the 0.00000000754 newtons, very small amount of force of attraction. And so, but it works over long distances. If we think of planetary motion, the force of gravitation acts over a very long distance. And so that's one of the fundamental forces, the force of gravitation. But then in the nucleus, we have the strong nuclear force, and that is, again, stronger than the electrostatic force, and that's 2 and 3, the fundamental forces. And the strong nuclear force is stronger than the electrostatic force. However, it only works on a very, very small range, very small distance. Those particles, as soon as those particles start to separate here, if the nucleus just separates just a little bit, the electrostatic repulsion will cause the nucleus to go apart quickly. But yeah, as long as it's a very, very small distance, it's the strongest out of the fundamental forces and holds the nucleus together. So by shooting electrons and protons at the nuclei, scientists were able to determine the size, approximate size of the nucleus, and they determined that the density of the nucleus is the same for all nuclei, no matter how big the nucleus is. We've got the same kind of density. And nucleons can only interact with a few nucleons at a time because of the short range of the force. So, if you have, let's say, a uranium nucleus, let's say you had 235 nucleons, I would have to do 235 circles here. This nucleon right here, whether it's a proton or a neutron, is not even interacting with this one in terms of the strong force. It's only interacting with the ones that are close to it. And whereas, with the electrostatic force, that can work over a longer range. And so, but again, the strong nuclear force is holding that nucleus together, overcoming the electrostatic repulsion. So what if there are too many neutrons or protons in the nucleus? We have a nucleus here with protons and neutrons is representing, a nucleus here. What ends up happening is that the weak nuclear force, which is the 4th fundamental force that we're talking about, changes protons into neutrons. It also can change neutrons into protons. If there are too many of one kind, it can change, the weak nuclear force can change from one to the other. And as we get into elementary particles, which will be the next unit, we'll talk about the weak nuclear force in more detail and how that exactly happens there. So if we summarize the forces, this would be good to have down in your notes. We have the 3 forces that are working in the nucleus. We have the electromagnetic, we have the strong nuclear, and then we have the weak nuclear. And the electromagnetic in the nucleus works on protons only. It's trying to push the protons away from each other. the range is infinite. So, it doesn't matter how far apart those particles are in the nucleus, we have that amount of force. Now, relative strength is helpful here because what this is comparing it to is the strength of the electromagnetic force compared to the strong nuclear. And we know that strong nuclear is stronger. It's between the protons and neutrons. It's attractive. It's over a very short distance. And so the relative strength is 1. So the electromagnetic force is 1/137th as strong as the strong nuclear. And that gives you an idea of how much stronger the strong nuclear is. But again, it only works over this very, very short range. Now, the weak nuclear force is on protons and neutrons. It's attractive and repulsive. It's over a very short distance, 10 to the negative 17th meters. And you can see it's, by far the weakest here, 10 to the negative 6th, as compared to the electromagnetic and the strong nuclear. The weak nuclear, again, is responsible for changing the protons into neutrons and neutrons into protons in the nucleus. So at the end of the 19th, beginning of the 20th century, we started to discover what's going on with nuclei in more detail, and Marie Curie was very instrumental in helping us understand what's happening. And so, she and other scientists discovered that some nuclei are unstable, and those nuclei emit particles and become different nuclei. And this is radioactivity. And as Marie Curie worked through these experiments, she was very instrumental in the discovery of much in radiation and better understanding the elements and what's happening in terms of the change of nuclei as they go from become one or different kinds of elements through the decay cycle. So in a nuclear decay, they're random and spontaneous, and where an unstable nucleus ejects a particle and changes to another nucleus. And so there's alpha decay, which we'll talk about. There's beta decay. There's 2 types, beta minus and beta positron decay. And we'll also be talking about fission, where a nucleus splits into 2 fragments, and fusion, where nuclei combine together to form another nucleus. The other type of decay, it's not ejecting a particle, but it's also ejecting gamma ray, and that's another type of decay we'll talk about. So with alpha decay, they found that these were positive emissions, where a nuclei of helium, 2 positive 2e, 2 protons, 2 neutrons, was shot out from a nucleus. And those particles came into contact with electrons, and by analyzing the spectrum, they found that these were alpha particles. And so using the quantum physics that we've learned, to be able to see that these were helium nuclei. So here's a visualization of that. We have a plutonium nuclei that ejects a alpha particle, and as it does, becomes uranium. And so this is how we would write that out. We have the nucleon number here, we have the proton number here, and afterwards we have a helium nuclei, which is 2 protons, 2 neutrons, and then we have what's left, which is the uranium nucleus, which you can see here. And so alpha decay occurs only with very heavy elements. You can see here with plutonium 239, it's a lot of nucleons there, and and we can see the charge here is positive 2. We have the charge down here. So the discovery of the alpha particle, and Rutherford and Royds in 1909 collected gas samples, alpha particles produced, or collected gas alpha particles produced, and then looked at the light produced when it came in contact with electrons, and discovered it was helium atom that was actually shooting out, helium nuclei, and then when coming in contact with electrons, they can become neutral atoms, and then as those atoms get excited, they can electrons will go to the outer energy levels, drop down, and shoot out photons of light. And so we have very, very specific photons of light that are